The thing that's on my wall right there, it's a prism. So let's back up a little bit. You all know that the light that you see with visible light, white light, is made up of a bunch of different colors, and it behaves as a wave. And if we send that wave of white light into a prism, it gets split apart. Do you know why? Good, out in the hall. When we send light into a prism, just like a band of marchers going around a corner, the light bends. And the different pieces of light are moving at different speeds. So the further they go, the further they bend apart. Now let's back up again to speed of light, c. Remember, we know that light behaves as a wave, right? This goes back long before any of the particle physicists we were talking about. And we can describe the behavior of light with this equation, c equals lambda v. Okay, well c we know is speed of light, sometimes called SOL, speed of light. V is our frequency, and lambda is our wavelength. Okay, great. What does any of this have to do with the lab, Moser? Come on. We're getting there. So remember, what is frequency when we're talking about measuring things on a wave?
Isn't it the point between two?
You're thinking of wavelength. You've got the other half of it. Good. Frequency is how often something happens in simplest terms. So with a wave, frequency is how often a trough passes a given point, or a crest passes a given point. So it's how many waves hit that thing every second. And we usually measure frequency in, cycles per second, number of waves that hit per second. Wavelength, the other piece that you were thinking about, is the distance from one trough to the next trough, or one crest to the next crest. Slightly different. So when the wavelength increases, the frequency decreases. The longer that wave is, the fewer of them will hit that point every second. Okay, great. Whatever, Moser. Come on, we're getting old here. So we've got this equation. So speed of light is the same for all forms of light. Doesn't matter what color of light it is, moves at the same speed. Anybody actually know the speed of light off the top of their head? No. We usually give it as 3 times 10 to the 8th meters per second. 3 times 10 to the 8th meters per second. Now, interesting thing about these little colorful bits of light, these little sort of, pieces of rainbow captured. If you look in your book on page 92, and you don't have to, but I'm going to tell you that red light has a different wavelength than blue light. So the red end of the spectrum, these are relatively long wavelengths. These are like 700 nanometers. And the indigo, the very low end, the violets, are about 400 nanometers. Okay? Well, that means that if they're all moving at the same speed, and we know their wavelength, we can figure out the frequency for any of them, right? It's 3-part algebra. Go us. We can do this. Yeah? Good. Awesome. Easy. What does this have to do with the lab? So switching gears for a second, your lab tells you that E equals HV. Some of you, a lot of you, had this H in your presentation. H is what? Planck's constant. Planck! Good old Max. Well, so this is a constant. We can figure out frequency of any piece of light. Can we figure out how much energy a single piece of light has? Yeah, we can. We can figure out how much energy a ray of red light or a ray of purple light has. That's Cool. What does this have to do with atoms? Huh? We're getting there. What is that? It's a hydrogen atom. It's a single proton and a single electron. It's a little old hydrogen atom. Our buddy H. So if we went back to that spectrum analyzer and we stick this thing in the spectrum analyzer, let's go do that for a second. So what good old Niels came, oh yeah, I'm sorry, I gave it away. I was going to say, whose model of an atom is this? Bohr! I'm sorry, are you bored? So, Niels says, you know, when we put hydrogen in the spectrum analyzer, we run some current through it, and it glows that pretty pink, and we can break it down, and we can get 5 lines out of it. This is like an apartment building. And there is some second floor. And this electron can climb to the second floor when we give it enough energy. This is like you going from standing on the floor to standing on your desk. We can push that electron up to the second floor. But then when it falls back down, it gives off that light. And the amount of energy, whoa. So the amount of energy that's given off in that light is the difference in energy between this floor, this energy level, and that energy level. That's all Bohr was saying. You know, so that's why the hydrogen emission spectra actually fits better with his work than with Planck's, even though Planck was the first one who really utilized it. Bohr is the one who uses it to explain the structure of the atom. Okay, great. Now, let's answer some questions from the lab. Looking at the spectrum analysis thing that we did, if you had 2 colors that were really similar, like you had Li and Sr that were really similar, and a lot of you did a really smart thing, is you thought your unknown was one of these 2, so you went and got another sample of the unknown and a sample of this and a sample of this and burned them all right side by side so that you had a better view to compare. Well, what if you had sophisticated equipment? Let's go to the spectrum analyzer. Okay. And this is a little bit beyond what the lab asks you for, but it's good practice. So what if I gave you a wavelength of light and told you I wanted you to find the energy. And I wanted you to do it in one equation. So how would you find the wavelength, or how would you find the energy of a piece of light? Let's say I give you a 512 nanometer piece of light. That's somewhere in the bottom of that's like bluish. I said, I want you to find the energy of that. How would you go about that? Without any restrictions on how many equations you can use. Well, remember, this is frequency. This is wavelength. You're on the right track, though. You have to get frequency. So, what? You can plug this in here, rearrange, C over lambda equals V. Okay, and then plug that number in there. If you were to do this in one equation, can you? Who's going to take physics with me next year? Who's in for the full ride? It's a lot of fun. We do something called substitutions a lot. So we go, oh, well, this is equal to V. I can plug that in for V. Gesundheit. So E equals HC over lambda. It's just substitution. It's just making a larger equation out of 2 smaller ones. So we can actually, and C, of course, is speed of light. It's a given. It's a constant. We know it. We can look it up. It's, it's just out there. So this is one way that from a given piece of light, without having its frequency, you can find the amount of energy contained in it. Okay?